One way you can really boost your progress in electronics is by getting to know more and more electronic components. It doesn't matter if you are into repairs, design, or other fields. The more familiar you are with electronic components and the more you have worked with them, the easier it will be for you to advantage. In this video, in addition to the 27 components you learned about them in previous parts, you are going to get familiar with 6 new, very useful and exciting electronic components. You will understand how they work so you can use them in your projects or find faults in them more easily during repairs. If you want to level up your component knowledge, stick with me until the end of this video. This video is sponsored by PCBWay.com. Alright, my dear friend, welcome to the 5th part of our basic component series. The components we have covered before in previous parts were mostly general purpose components that you can find in almost any project. Among them were a few sensors too, like light sensor, resistive temperature sensors, and similar ones. The components we are going to look at in this video are also mostly sensors. Alright, let's not waste any more time and get straight to the main topic. Component number 1, reed relay. Reed relays are a type of magnetic sensors that close a switch when the magnetic field increases. We will take a closer look at them and then we will come back and talk about their applications. These components you see here are all reed relays. If I bring a magnet close to these reed relays, I can hear a clicking sound, which is the sound of the reed relay contacts switching. So when the magnet comes near it, the two contacts inside this reed relay, these two contacts become magnetized and connect to each other, causing the two terminals of the reed relay, which you see here and here, to connect. We can switch almost anything using these reed relays, like a DC motor, AC motor, a buzzer, or similar things. Let me bring a 12-volt DC motor and use the reed relay to switch it to see if it works. I want to build exactly this circuit. You see that when I bring the magnet close to the reed switch, the motor starts working, meaning the connection between the two pins of the reed relay is established. And when I move the magnet away from the reed switch, the motor stops, meaning the reed relay has disconnected. This type of the reed relay is called normally open. That is, when the situation is normal, the terminals are not connected and they connect when the sensor is activated. All three of these are schematic symbols for reed relays, each for a specific type of reed relay. This one is a schematic symbol for a normally closed reed relay where the connection between its two terminals is established in normal state and it breaks when a magnet approaches. This one is the normally open type where the connection between two terminals is not established in the normal state and they connect when a magnet approaches. And this one is the double through type, which has 3 pins, a common pin here and a normally open pin and a normally closed pin. In the normal state, the common pin is connected to the normally closed pin and not to normally open pin. When a magnet approaches, the connection between the common pin and the normally closed pin breaks and the connection between the common pin and normally open pin is established. I'll do another experiment. This time I want to use the normally closed state of a double through reed relay to switch a 3-volt DC lamp. Now I want to set up this circuit. Here you see that when the magnet comes close to the reed relay, the lamp turns off, and when the magnet moves away from the reed relay, the lamp turns on. You know what I am thinking about when I see this circuit? Yes, exactly. The light inside a refrigerator. If we embed the reed relay inside the frame of a refrigerator and embed the magnet inside the refrigerator door, we can automate the refrigerator light. For example, when we open the refrigerator door, the magnet inside the door moves away from the read relay, causing the lamp inside the refrigerator to turn on. And when we close the door, the magnet comes close to the read relay and turns the lamp off. If you think more, you can find other applications too. For instance, you could attach it to your room door and build a sensor that detects when the door is open and say, sounds an alarm. It's also used in other places, like inside water pumps to detect water flow. A magnet is placed inside the pipe in the water's path, and when water flows, the magnet moves away from the read relay. The system then detects that someone has opened the water tap and the pump should now turn on. Even though the read relay is a good component and can be considered as a usable magnetic sensor, this component also has several major drawbacks. First, it's a mechanical component and doesn't have very high speed. So, in applications where very high speed is needed, you can't rely on this component. Second, the output of this component is somewhat digital, meaning it only turns on or off, and it only shows us two states, whether the magnet is near the sensor or not. This component can't tell us how close the magnet is to the sensor. To solve these two problems, we can use the next component. Component number 2, Holifix Sensor. A Holifix sensor is an electronic component that tells us not only the presence or absence of a magnetic field, but also the strength and polarity of the magnetic field around it. All of these are Holifix sensors available in different packages and different part numbers, and they have varying specifications. One of the most common type of these sensors is this UGN3503, which has pins like this. Pin number 1 for positive supply, pin number 2 for ground or 0 volts, pin number 3 for the output. If we apply appropriate voltage, meaning a voltage between 4.5 volts and 6 volts to pin number 1, 0 volts to pin number 2, the sensor will start working and show us the amount of magnetic field around the sensor as a voltage on the output pin. If the magnetic field around the sensor is neutral, it will give us an output voltage of roughly half the supply voltage. For example, if the supply voltage is 5 volts and the field around the sensor is neutral, it will give us approximately 2.5 volts. And if there is a magnetic field around the sensor, depending on the polarity and density of the magnetic field, the output pin voltage might become less or more than 2.5 volts. This sensor is pretty cool, right? I really like it. You can implement so many ideas with this sensor. It's a powerful tool. I think it's better if we build its circuit once and practically test it together to get more familiar with its operation. This circuit is the simplest one you can use to test the Holifix sensor. We connect the supply voltage to pins number 1 and 2 and output to multimeter to see how it performs. You can see that in a normal situation there is a voltage around 2.6 or 2.7 volts in the output. Now if I bring the magnet in front the sensor, you can see that the output voltage decreases, and if I bring the same pole from behind, it will increase the output voltage. If I use the opposite pole in front the sensor, it will increase the output voltage, and from behind it will decrease the output voltage. So this pole from behind will decrease the output voltage, and this pole from behind will increase the output voltage. The sensor we just tested, even though it gives us a voltage output that changes with the strength and polarity of the magnet, this voltage doesn't have much power and can't provide a high current. To use this sensor, you need to connect the output voltage to an amplifier or feed it to an analog to digital converter to convert it into a digital value so you can use it. I personally really like 3-pin sensors like this Holifix sensors that take supply voltage and show the parameters value as a voltage on one pin. Do you know another example of these 3-pin sensors that I want to introduce you? Yes, you do. But before we jump back into things, I want to quickly introduce you to our fantastic sponsor of this video, PCBWay.com. If you are into electronics like I am, you know how crucial high quality PCBs are for bringing your projects to life. And honestly, PCBWay is my choice. They offer top quality PCB manufacturing and assembly services at really competitive prices, and their quality is just chef kiss. Plus, their online ordering process is super easy to navigate. So, if you are got a project coming up and need a reliable PCB, make sure to check out PCBWay.com. I have put a link in the description below for you. Anyway, let's get back to the components. Component number 3, LM35 temperature sensor. The LM35 temperature sensor works exactly like the Holifix sensor. That is, you just need to connect the supply voltage to it and it will give you the ambient temperature as a voltage on its output pin. If you look at the datasheet, it says that this LM35 temperature sensor is available in several different packages. One is SO8, which is this one. This is an LM35 temperature sensor. Another one is TO92, which is this. And there are two others, TO46 and TO220. But the most common one is TO92. If you look closely to this package, I mean TO92, we see that the pin out of this sensor is different from the UGN3503 Holifix sensor. Here, pin number 1 is for positive supply, pin number 3 is for negative or 0 volts, and pin number 2 is the sensor's output. However, this difference isn't the only one between the sensor and the Holifix sensor. Surely, other than the physical quantity that the sensor detects, their supply voltage range also differs. With the Holifix sensor, we had to supply a voltage between 4.5 volts and 6 volts, but here we can supply a voltage between 4 and 20 volts, the supply pin here. The next difference is that the sensor's output voltage here has a linear relationship with the ambient temperature. This means if we multiply the output voltage by 100, we will get the approximate ambient temperature. This means that for every 1 degree Celsius, this sensor generates 10 millivolts as an output on pin number 2. For example, for a temperature of 15 degrees Celsius, it generates 150 millivolts or 0.15 volts on the output pin. If we multiply this number by 100, we will get 15, which is the ambient temperature. Or for instance, if the sensor generates 370 millivolts on the output, it means that the ambient temperature is 37 degrees Celsius. I'm going to test this sensor practically to see exactly how it works. I'm going to set up this circuit and test the component. I'll connect 5 volts to the supply and the output to the multimeter. You see that the voltage it generates on the output pin is around 248 millivolts, which means that the sensor's temperature right now is 24.9 or 25 degrees Celsius. Now, if I use this lighter to increase the sensor's temperature, the output voltage will increase. See, the output voltage increased, meaning the sensor's temperature went up. Now, if I use this freeze spray to lower the sensor's temperature, the output voltage will also go down. See, the output voltage is going down. Now, I'm gonna spray more and more to see how low the output voltage goes. It won't go below the 0 volts. Why? What does it mean when the sensor's output voltage doesn't go below 0 volts? Does it mean that the sensor's temperature didn't go below 0 degrees? Of course it did, right? With the freeze spray, the sensor's temperature gets much lower than 0 degrees. That freeze spray can even bring the sensor's temperature down to negative 40 degrees. So why didn't the sensor give us a voltage less than 0 volts? Can't this sensor measure negative temperatures? Of course it can. This sensor can measure negative temperatures. With the circuit we have built here, we can't measure negative temperatures, but that doesn't mean that this LM35 sensor can't measure negative temperatures. If we refer to the datasheet for this sensor, we will see that it suggests another circuit that can measure negative temperatures. Look here, I mean this circuit here. The datasheet says that by using this circuit, we can measure negative temperatures even down to minus 55 degrees Celsius. I leave it up to you to test the LM35 sensor at negative temperatures. If you test it yourself, please tell me the result in the comment section. Anyway, the next item I want to introduce is a very interesting but also scary sensor. Component number 4, gas sensor. A gas sensor, as its name suggests, is a component for detecting the presence of gas in the environment and even measuring the concentration of different gases in the environment. Usually, each sensor can detect a unique gas, although it might be able to sense other gases, but generally, different sensors are made for different gases. For example, the MQ4 sensor is used for measuring methane gas concentration, and MQ6 sensor is used for measuring LPG gas concentration. Gas sensors typically look like this, though other shapes exist, but you will often find gas sensors in this form. A 6-pin component used for measuring the concentration of a specific gas in the environment. For example, this is an MQ5 sensor which can help us measure LPG gas. As I said before, this sensor has 6 pins. Pin number 2 and 5 are used for heater, and pins number 1, 3, 4, and 6 are used for measuring gas concentration. By the way, these gas sensors have a built-in heater to heat up the sensor because they need high temperature to work properly. 2 of these sensors pins, pin number 2 and 5, are used for the heater. That's why I say the sensor is little scary, because when a beginner uses the sensor, they see that the sensor gets hot and smells like burning, and many people immediately think the sensor is broken and cut off the power to the circuit. You might ask how a beginner could possibly set up this sensor. Surely they have studied the datasheet and seen that there is a heater inside the sensor. I have to tell you that no, many beginners uses module instead of the sensor itself. This is a gas sensor module. Instead of 6 pins, it has 4 pins. You just need to connect 5 volts and 0 volts to the supply pins, which are labeled as VCC and ground here. Look here. This is VCC and this is ground for the module to start working and give you the concentration of the desired gas on the analog output pin as voltage. Look here. This is a 0 pin, which is analog output pin. I'm gonna test it. I'll connect 5 volts and 0 volts to the supply pins and analog output pin to the multimeter. Now our sensor is hot and you can see a voltage on the analog output pin. If I expose this sensor to LPG gas using this unlit lighter, you will see that the analog voltage changes. Look. It works. There's also a digital output on the module. If the gas concentration goes above a certain limit, the digital output activates, and if the gas concentration is below that limit, the digital output is off. In this video, I don't want to talk more about the module. I mostly want to talk about the sensor itself. This circuit is the simplest way to get a gas sensor up and running. You just need to apply 5 volts to the heater supply, I mean pins number 2 and number 5. Then you need to put a 27 kilo ohm resistor and pins A and B in series, and then connect a 5 volt supply to the circuit of the 27 kilo ohm resistor and pins A and B. With this, the voltage across the 27 kilo ohm resistor will be directly proportional to the gas concentration. Here you see that when I expose the sensor to the LPG gas, the voltage across the load resistor changes. This is enough for us to measure the gas concentration with it. Setting up a gas sensor seemed a bit more complex than the previous sensors, right? That's nothing. Things get more complicated when the frequency goes up. In the sensors we have looked at so far, the frequency of the parameter we want to measure was very low. For example, temperature, gas sensor, or even magnetic field changed slowly, right? If we want to measure a parameter whose changes are very fast, the work becomes even more complex. Component number 5, sound sensor. I say that if the frequency of changes is high, things get a bit more complicated. For example, if you want to process sound in the environment, whether it is recording it or amplifying it or anything else, you need a sensor that can sense the sound in the environment and deliver it to us as an electrical signal. This is done by a microphone, which is a type of sound sensor. This is the schematic symbol for a microphone which you can use in many projects. Microphones can convert the sound waves that hit them into electrical parameter for us. Sound waves are mechanical waves, not electromagnetic waves. They are mechanical waves that are transmitted through vibration of air molecules. They hit the diaphragm of a microphone and appear as an electronic parameter on the 2 pins of the microphone. As you can see, a microphone is a 2-pin component that seems very simple. And this is the diaphragm of a microphone inside it, which is very similar to a mirror. Look. If you think the output on the microphone pins is voltage, you are right, but the voltage signal at microphone terminal is very weak. It is true that for processing audio signals, we eventually need the audio signal to be in the form of a voltage, so we can work with it. But for simplifying the process of using a microphone, it is much better to pretend the signal is not in the form of voltage. It will make the process super easy if you assume that the sound signal at the microphone pins is a form of varying resistance. So we are going to believe that the sound signal across the microphone terminals is in the form of a varying resistance. If the audio signal in the environment looks like this, the resistance between the 2 pins of the microphone will increase and decrease exactly with the same shape like this. You probably know that we can't directly use resistance changes for processing audio signals or any other type of signal. We need to somehow convert these resistance changes into voltage changes. Believe me, there is no contradiction here. We actually need to assume that the voltage changes are resistance changes, then convert the resistance changes to voltage changes to make things simple. Actually, it makes circuit and understanding the circuit much easier. Converting resistance changes of this microphone to voltage changes isn't very difficult. You just need to put the microphone and a resistor in series and connect the power supply across the 2 ends of the circuit. I mean this point and this point. Now we can get the audio signal as a voltage from the output point. I mean this point here. To test the microphone, I want to build the circuit and see if I can see the audio signal on the oscilloscope or not. Look here, when I talk, we can see the waveform of my voice on the oscilloscope. In fact, we can conclude that the microphone is working correctly. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. It's working perfectly. I previously published a full video about microphones, so if you are interested in this topic, you can go and watch that video after this one. I'll put the link to that video in the description. The last point is that whenever you want to process the output signal of the sensor, you need to amplify the weak and low amplitude audio signal from the microphone's output using amplifier circuits so you can use it. Anyway, if you are one of those friends who think that microphone's output signal is very weak, I want to draw your attention to component number 6, antennas. I remember when I was a kid, an antenna was a symbol of technology for me. That is, when I saw a device with an antenna, I thought it was much more complex device than other devices without antennas. The bigger the antenna, the more respect I had for it. For example, I would have to bow down to a telecommunication tower. Just kidding about the last part, of course. These days, external antennas have given way to internal antennas. That means devices don't have a big antenna sticking out anymore. Instead, a small antenna is installed inside the device. Of course, the operating principles haven't changed at all. These are examples of different types of antennas that can be used in various devices. There are different antennas for different powers and different frequencies, but their operating mechanism is all the same. When electromagnetic waves hit a metallic object, they discharge some of their energy onto that metallic object. In fact, the electromagnetic waveform manifests itself as electrical energy and then as a voltage on that metallic object. However, the effect of all waves on all metallic objects isn't the same. That is, some waves with specific characteristics can have a greater impact on some metallic objects with specific alloys, shapes, or properties. That's why we have antennas with different shapes for different signals. The effect that electromagnetic waves have on antennas isn't very strong. They put a very small and subtle impact on the antenna's energy and electrical charge. But that's enough for us to receive the signal. The signal an antenna receives is a combination of all available signals in the environment with all frequencies. It is our art to come and separate the desired signal, which has a specific frequency, from all the signals the antenna receives using filtering circuits, and then amplify the desired signal using amplifier circuits. I think it's worth doing a test to see how exactly an antenna works. Here I want to connect the antenna to my oscilloscope in this way and then send a signal next to the antenna using this remote controller so that it can be received by the antenna and displayed on the oscilloscope. Here you see that when I press the button, the waveform sent by the remote controller is visible on the oscilloscope. In fact, the remote controller sends an electromagnetic wave. This wave, upon hitting the antenna, manifests itself as voltage changes with the antenna. Pretty interesting, right? The antenna's operation was simpler than you thought, right? Even more interesting is that any metallic object in the electronic circuit, even traces on a PCB, can act like an antenna and receive signals present in the environment, although I don't think that's a good thing. Usually receiving ambient signal by PCB traces causes interference in the circuit's operation, which we call it noise. For example, on this PCB, the pin headers here and here that are used for connecting the programmer or connecting the UR also acts like antennas and receive ambient signals. If the signals these pin headers receive or the signals received by the PCB tracks here are stronger than a certain limit, they will definitely cause interference in the system's operation and might even lead to a complete system shutdown. Of course, antennas aren't always for receiving receiving signals. They can be used in reverse to transmit signals in the form of electromagnetic waves into the environment, which also has its own specific techniques and methods. Alright, my friend, thank you for watching me. We have reached the final moments of this video here. If you like this video, please give it a thumbs up and subscribe to my channel so you don't miss the next videos. Until the next video, take care of yourself and have a good one. See you in the next video.